All right, welcome back everybody. In the previous video for the adiabatic CSTR, we had a brief overview of the process and we came up with a strategy of how we were gonna develop a dynamic model. Okay, in this video we're gonna apply all those apply the map, the quote-unquote strategy, the map that I made earlier. So once again, we have the schematic here, and let me just label it for you guys again. I have the insulation, we have the stirrer. Okay, now the stirrer is responsible for keeping it well mixed, just to make everything explicit for you guys so you guys can follow, and the insulation makes everything adiabatic. Okay, we have the information regarding the process. We have both the fluid properties that we're gonna need, as you can see, the average density, and the average heat capacity, the specific heat capacity. Let me just, so that I know these are a little, some people might think they're insignificant details, but there's a difference between specific heat capacity and heat capacity. And what is that difference? I encourage you guys to do some research on that. Just a little homework. Of course, we have our upstream variables, the inputs to our system. Upstream variables and input variables. These two terms are used interchangeably for a controls problem. Input variables. Also, we have the kinetics. We have the kinetics information for our reaction. All right, we have some non-linear kinetics. All right, let's since we're really good engineers, we're gonna start off by explicitly listing our assumptions. Our first assumption being that we have a well-mixed system. Well-mixed. All right. And for anyone who does not remember, the well-mixed system implies that all the spatial derivatives, the gradient, is equal to 0. Okay? Just so everybody's on the same page. Some of you might already know this. Some of you are like, oh my god, where the hell is this del operator? Where is this? What is this calc 3 terms? It just means there are no spatial variations. No spatial variations. Again, some of you might already know this. For some of you, this is going to be a good revision. No spatial variation. I have explained it both in English and mathematics. At least I've tried to explain it in English. All right. Now we also have adiabatic. Adiabatic. That's how you pronounce it. And the implication for that is the heat transfer is going to be 0. The rate of heat transfer with the surroundings is going to be 0. There's no heat addition, no heat removal from the system. With these assumptions, let us begin our model. So we're going to start off with our total mass balance. Writing a total mass balance for reacting systems is a good strategy because it's going to give you, I'm going to show you why it's a good strategy. Let's write this first. The rate of change of mass inside the tank is going to be equal to the rate of input density times the inlet flow rate minus the rate at which mass is leaving our stream. And I'm labeling all the downstream variables, all the unknowns. I'm showing right now that they can vary with time. Okay, so far we have one equation and two unknowns, and this method that I'm using here was developed by Dr. Carlos Smith, so credit given where it's due. All right, Dr. Smith. Now this equation is going to be responsible for the mass inside the tank. All right, the other unknown, the output flow rate, is something we're still looking for, right? Let's see what we can If we go back to our schematic, we know there's a valve. So every valve has a characteristic valve equation. I'm going to use the most, valve equation. I shall be using the most generic valve equation. The valve coefficient multiplied the pressure drop, the change in pressure across the valve, divided by the specific gravity. The specific gravity term, if you make it more explicit, this turns out to be 1000 multiplied by the pressure drop divided by the density of our fluid. Okay, and just so everybody's on the same page, just to give you a side note, specific gravity is equal to density divided by the reference density. And for most valves, the reference density is always water, in SI units, of course, and the term itself is dimensionless. But we're gonna be using GF because everything else here in the valve equation, we're assuming everything is in SI units. SI units, I like SI units. They make life easier. I like SI units. Nothing against anybody who likes English units, but I mean, come on. So we have two equations, and as you can see, we've added a new variable. So 3 unknowns. The second equation shall be responsible for giving me the output, the outlet flow rate. Now I need an equation to give me the pressure drop across the valve. So the pressure drop across the valve, pressure change, pressure drop, same meaning. Delta P of T is equal to the upstream pressure minus downstream pressure. And this is the same thing. This is exactly the same thing as in some textbooks it will be written as P inlet minus P outlet. Exactly the same thing. There is absolutely no difference. All right. So the inlet flow rate, let's go back to our example. I'm assuming that the overhead pressure is equal to the atmospheric pressure. So the total upstream pressure is going to come from the overhead pressure and the height of the fluid, the hydrostatic pressure, okay? And we're discharging our contents at atmospheric pressure. Therefore, delta P of T turns out to be P ATM, atmospheric pressure, plus the hydrostatic pressure, minus P ATM. And since you guys are so good at mathematics, we're just gonna do some algebra action, and here we are. Okay, now let's see. We've added an other unknown. How are we gonna find the height inside the tank? No worries, we're gonna get there. 2 unknowns. Okay, so far we have 3 equations. 4 unknowns, because I've added the height is my new unknown, right? So the third equation shall be responsible for giving me the pressure drop across the valve. Now I need a new equation for the height inside the vessel, the height of fluid inside the vessel. And this can be very easily done by the height inside the tank. The height of the column shall be equal to the volume of the reactor contents divided by the cross-sectional area. Okay, now that is a simple geometry problem. I hope you guys can follow. 4 equations, 5 unknowns, and this equation shall be responsible for giving me h of t. And now there's another unknown that I've not explicitly accounted for. Some of you guys have already looked forward and know exactly what to do. But there are going to be people who have no idea where to get volume. And to those people, I say, it's okay. We're going to work through this. Volume inside the tank is equal to mass inside the tank divided by the density. We have, as you can see, in the very first equation, we have already accounted for the mass inside the tank. Therefore, our degrees of freedom have reached 0. And the fifth equation shall be responsible for giving us the volume of the contents of the vessel, right? Okay, now so far we've had a total mass balance, and we have enough information to model the hydrodynamics, how the level, the discharge flow rate, etc., the hydrostatic pressure, etc. But in a reacting system, I'm concerned with the outlet concentration, and I'm also concerned with the outlet temperature. So we need those because this is an adiabatic CSTR. We have a stir tank reactor. All right, now mole balance on A. I'm just gonna do mole balance on A in this video, and I encourage you guys to do a mole balance on B by yourself by using the correct stoichiometry. Okay, d dt, and I'm gonna write moles as concentration multiplied by volume, just to save me some time. The outlet concentration multiplied by the volume in tank. The contents inside the vessel are at the outlet conditions. Why? Well mixed, because the system is well mixed. And this shall equal my inlet flow rate. I think let's go back and see our inlet flow rate once again. CAN. And let me just make sure the inlet temperature is also specified. Good, very good. CAN multiplied by QN minus CA out, our upstream variable, and Q out, both are our upstream variables. Downstream variables. These are the output variables, the downstream variables. Keep in mind, upstream is input and downstream is output. Just keep that in mind. Okay, all right. Okay, inlet flow rate, outlet flow rate. Now we also need the kinetics term, K times, now K multiplied by, okay, I remember my kinetics, the non-linear kinetics, multiplied by the volume inside the vessel. Okay, let's see. Another equation, 6 equations now, but we have 2 new unknowns. So we have a total of 5 plus 2, 7 unknowns. 6th equation shall give me the outlet concentration. But I need an equation that models the variation of K with respect to the temperature. Because we have an adiabatic reactor, we are not operating isothermally, so I need something that maps the effect of temperature on the rate constant. And luckily, if you've taken reaction engineering, or if you've even taken general chemistry, some of you might remember the good old Arrhenius equation. K is equal to a pre-exponential factor, e raised to power the activation energy divided by RT. All right. Okay, now a quick note, something that you guys need to note. Of course, this is going to be at the outlet temperature, but since whenever you multiply something with the ideal gas constant, you always use absolute units. So I'm just gonna make sure that everything is in Kelvin. Just to remind you guys that T in Kelvin is equal to T temperature in Celsius plus 273.15. Again, stating the obvious so everybody can follow. All right. Well. Now we've taken care of K, and we still don't have an equation for the outlet temperature. The outlet temperature is, in fact, let me make it more explicit. The outlet temperature is a downstream variable. Therefore, it's gonna vary with time in our model. seven equations and 8 unknowns. Okay, the seventh equation will be responsible for giving me the rate constant. I need a new equation for T out. The outlet temperature. How does the energy involved from my reaction? I'm wondering what equation I can use to model that. And some of you are way smarter than I am, therefore you already know that it's going to be energy balance. Now the energy balance, this is just going to be the rate at which the internal energy of the system is changing, and that shall equal to the rate of enthalpy flow rate into the system, rho Cp times the inlet flow rate, just to make sure our unit's correct, rho Cp Q in times T in minus T reference minus Q out, rho Cp Q out times T out minus T reference, and the energy, the enthalpy term due to the reaction. Okay, now I have a question for you guys. I have a negative sign here, and the reaction is exothermic. Now this is a critical thinking question for you guys. I have a negative sign here and the reaction is exothermic. Will there be generation of heat or will there be consumption of heat? That's a question for you guys. ddt times rho Cp volume in tank multiplied by T out minus T ref. Okay, now the equation is getting long, but so what if it's getting long? It's just an equation. Okay, it just models it is just a conservation of energy, nothing more, nothing to worry about. Oh, Q out, where is with T? Where is with T? Okay, T out T minus T ref, and of course our enthalpy term, and it's up to the reader to decide whether this is going to be a consumption term or a generation term. All right, so how many equations do we have? 8 equations. T out was the unknown that we were accounting for. Have we added any new unknown? Nope, there's no unknown. T reference, some of you might ask T reference, but guess what? T reference is arbitrary. T reference is arbitrary. You can choose, which means that you can choose whatever you want. Choose whatever is reasonable, just to make it explicit. All right, 8 equations, 8 unknowns. The 8th equation shall be responsible for the outlet temperature. And there you go, ladies and gentlemen. We have a total of 8 equations. Hold up, sorry. We started off with the mass balance, the dynamic mass balance, a simple in minus out accumulation equals in minus out, total mass conservation. Valve equation was able to give us the outlet flow rate. We needed to model the pressure drop across the valve, and that turned out to be the hydrostatic pressure. Okay, and in order to get the hydrostatic pressure, you needed the height. The height was given by the volume divided by cross-sectional area. Volume of the tank is equal to the mass inside the tank, which was already accounted for in the first equation, divided by the density. Mole balance, a simple mole balance that includes the inlet, the outlet, and the consumption term, because A is a reactant. And I encourage you guys to practice by writing a mole balance on B as well, by using the appropriate stoichiometry. And the Arrhenius equation gave us the rate constant, its dependence on temperature. And the outlet temperature was given to us by our dynamic, well-mixed energy balance. So I hope this was helpful for you guys. We're gonna do a couple of more modeling problems, and after that we're gonna move on to solution strategies. All right, thank you for your kind attention.